Hi, this is a continuation of the introduction for our unit on spectroscopy as imagery. Again, this is a web book that's up on our website. It has links in it. The idea behind this, again, is to always be looking at the link to the database that we have, the spectral database that we're linked into. It's called the Integrated Spectral Database. It comes out of Japan, and it's an absolutely outstanding database. What you want to do is look at lots of proton spectra, not carbon-13, but proton spectra, so that you start to understand the topography and the landscape of different functional groups or compounds that possess different functional groups. Now, what does NMR involve? NMR is a much more complicated technique than IR. It involves a magnet and radio frequency. And basically, you have to start thinking about molecules as having little magnets in them. Spinning charges are magnetic, and the hydrogens in molecules are magnetic. And when you put them in a magnetic field, they behave in a very distinctive way. They sort of get ordered. And some of the hydrogens, which are little magnets, align themselves with the magnetic field. Most of them do that. And then some of them align against the magnetic field. And what the experiment entails is putting the correct radio frequency in to make the hydrogens that are aligned in the favorable orientation flip over and go into the disfavored orientation. Then you take the energy away and the hydrogens cascade back down. So again, the magnet orders the little magnets, which are the hydrogens, and there are other magnets as well. The energy is radio frequency, and it pumps them up into a higher state. And what's interesting and what makes each hydrogen unique is that each hydrogen is at a slightly different magnetic field, or sometimes a drastically different magnetic field, depending on its environment in the molecule. And that theory is going to be discussed in class. We can't cover that in 3 minutes, okay? But what we're going to talk about here is what are you looking for in an NMR, okay? So what you're going to do is take each functional group and then go on the web and look at spectra. And we've also included some spectra in this document that you can look at. The more spectra you look at, the more you'll get it, okay? NMR is a little tougher, but an NMR spectrum looks basically like this. It goes in the other direction. It goes from 0, this is a proton NMR. We're not going to be doing other types of NMR this semester. 0 to 12 parts per million. And what we're going to talk about here is a little bit about positioning and a little bit about what you expect for a couple molecules. So for example, supposing I had this molecule. I'm going to do something very simple. Something like that. The only thing you're going to see in an NMR, in a proton NMR, are the protons. You're not going to see anything else. IR, by contrast, you see, in IR, you see the bonds. In IR, you look at the bonds in the molecule. In NMR, you only see the protons, because these are the little magnets that are undergoing that flip. Okay? Now, NMR is very rooted in symmetry. So basically, you see a different peak for each type of hydrogen in the molecule. And you're going to have to do a lot of functional groups before this really starts to sink in. In this molecule, you have 3 different types of hydrogens. So I'm going to call these the A hydrogens, this the B hydrogen, and all of these are the same. And I want you to think about, what do you know about symmetry? Most people do understand symmetry inherently. These hydrogens here have a slightly different neighborhood than this one here. And these two have a rather drastically different neighborhood because they're near that bromine. So what I would expect in this NMR is I would expect 3 positions. Okay? These kind of hydrogens, which are just kind of like alkane hydrogens, are going to be around. This is very approximate because I don't want you memorizing numbers yet. It's going to be around 1 ppm. So a run-of-the-mill hydrogen is around 1 ppm. These hydrogens, on the other hand, are going to be greatly affected by this bromine. It's going to really change their electronic density, and that changes the magnetic field they experience. So these hydrogens are going to be at about 3.5 to 4 parts per million. How are we with time right now?
5 minutes.
Okay, good. So this is 3.5 to 4 parts per million. And by the way, ppm, these are parts per million here, are proportional to frequency. So this means it's the opposite of IR. When you're going in this direction, the frequency is going up. So this little guy here, HB, is going to be somewhere in between. I would predict it would be at about 1.5. Now, you could sit with a table and you could memorize this every frequency. That never works. What I want you to do is go into the database and just keep looking up halogen compounds until you start to see the patterns of where things are, okay? So I'd expect these to be around 1, so I'm just going to put a little tick mark at 1. My scale is just terrible here, but I'll put a little tick mark there. I'd expect these to be somewhere in between. I'll put them like maybe about here. And then I'd expect, if this is 3, I'd expect these guys to be here, okay? The complicated thing about NMR is that in NMR you see a phenomenon that's known as splitting, okay? And it tells you about how many neighbors you have. So these C's, C would be here. These C's are actually going to be a doublet. I'll give you a little bit of information about that. These B's are going to be a multiplet because they're next to a lot. I'm just going to make kind of a messy looking multiplet here. And these A's are also going to be a doublet. It's getting a little complicated there. So initially, when you're working with this, you want to be very focused on position, what I tell you about position in the text, and then looking for it in the spectra. Like, come out of it and say, what can I say about halogen compounds? So if I drew another halogen compound, a simpler one, like say I drew this one, okay? If you had that, you should be able to say there are going to be two different peaks because there's 2 different types of hydrogens. These should be at about 3, should be farther, at higher frequency, at about 3.5, and these should be maybe around 1 or 1.5. You'd expect 2 peaks. Now the splitting comes from the neighbor. So you always see one more peak than the number of neighbors. So these, which form one group, have one neighbor. A neighbor is on an adjacent carbon. You see one more peak, so you see 2 peaks because there's one neighbor. You'll understand why this is so someday. Okay? These 2 also only have one neighbor. These are too far to be neighbors. The neighbors have to be living in the next house over, and the house is built of carbon. I always say that. Next house over. These only have one neighbor, so they are also a doublet. But this one has lots of neighbors. So you're going to see many peaks there. You're probably not even going to be able to define it. But I just want you to look at compound spectrum, compound spectrum, compound spectrum of the same functional group until you start to get it. This one, how many neighbors? 3. So you should see 4 peaks. This one, how many neighbors? 2, so you should see 3 peaks, but only 2 groups, okay? So again, the key to this is not analyzing it even at the detail that I've done here. The key to this is when you get to halogens, look at 5 spectra. I can't emphasize this enough. When you do alcohols, look at 5 or 6 spectra. Just keep going until you start to see the pattern in it. Okay, so we'll do more of this in class. Ask questions if you don't get it, because this is a little tougher. Thanks.